Hello folks, today is 6th of October and this is Dr. Shubhendu Bhattavyal bringing you a simple proof of the Pythagoras Theorem. Now, the Pythagoras Theorem, simple though it may be, what does it state? It states that if you have a right angle triangle like this with height h and width w and the hypotenuse hyp, then you have this relationship stated by the theorem, which is square of h plus square of w is equal to square of hyp, the hypotenuse squared. Now, simple though it may be, this is actually a very essential part of complex algebra in the two-dimensional plane. When you have the abscissa, the x-axis, and the ordinate, the y-axis. Here you can see that the base, which is labeled as w, is basically looks like the x-axis. The height, which is labeled as h, looks like the y-axis, and the intersection of h and w is the origin. So in a two-dimensional plane, you know the distance between 2 points with coordinates x1, y1 and x2, y2 is given by square root of x2 minus x1 whole square plus y2 minus y1 whole square. Now that relationship, that distance magnitude can be inferred from the Pythagoras theorem very easily. Now you can just picture x minus x1 as being the base and y minus y1 as being the height of a triangle, which is basically, you can visualize it as the triangle formed by the line connecting the 2 points and their and the drop downs or the drop down perpendiculars from those points onto the axis. So I don't want to go deep into that, but you can understand this very important theorem. The importance of this theorem is it is essential to our complex algebra. And so now the proof that we know, if you remember, the proof that we know of this theorem uses geometry, and it constructs squares on each of the sides. There's a square on the h side, square on the w side, and a square on the hypotenuse side. And by some means, by dropping perpendiculars and lines and a little bit complicated geometry, we prove that the sum of the squares on the vertical and the horizontal sides is equal to the square of the slanting side, which is the hypotenuse. So I don't, in this proof, we make it very simple. We just use basic relationships. What relationships do we use? We use, we use the area relationship. Now look at this triangle. If you want to find the area of this triangle, naturally you will start by using this formula. Area is equals to half into w into h. That's the natural instinct. But that's not the only way. We can turn it around like this. Look at it from this side, where the hypotenuse becomes the base and the origin point, the intersection of the x and y axis or the h and w axis, becomes the top or the top vertex. Now we drop a perpendicular from that top vertex onto this base, which is the hypotenuse, and there we have the second way of computing the area. Half the hypotenuse into L perpendicular. This L perpendicular is the length of the perpendicular dropped from the origin point onto the hypotenuse. Now, when we are looking at this particular area from these two viewpoints, the result must be the same. Therefore, we can say that W into H is equals to H by P into L perpendicular. Now, this means that L perpendicular is equals to W into H by H by P. It is as if you can see that the area of the rectangle H formed by the sides H and W is equal to the area of the rectangle formed by the hypotenuse and L perpendicular. So, so this gives us one simple way of finding this L perpendicular. This L perpendicular is the newcomer. The usual members of this diagram are H, W, and H, Y, P. L perpendicular is a newcomer. The L perpendicular is represented in terms of the other original members as WH by HYP. Now, this is one simple relationship which we use, the area equality, which means that no matter which way you compute the area, the result will be the same. Now, we have another component of this symmetry, a symmetry component in this triangle. Now, if you look at this triangle, the triangle has two angles. One is a alpha here, and the other is 90 degree minus alpha here, because the sum of all the angles of a triangle is 180 degrees. So now, if you look at the original triangle, then what the perpendicular line has done is the original right angle triangle has been split into two right angle triangles. The first right angle triangle is this one, the one on the upside of the L perpendicular line, and the other is this right angle triangle. This is on the downside of the L perpendicular line. So there are basically two triangles, two right angle triangles. By dropping a perpendicular from the origin, this is the origin, onto the hypotenuse, we've divided the right angle triangle into two right angle triangles. The first one is on the upside and this is downside. Now, because of symmetry considerations, it's easy to show that the angle here, the alpha angle, is also the same as the angle here. This is also an alpha angle, this angle. And similarly, the angle here, which is 90 degrees minus alpha, is equals to the angle here, which is 90 degrees minus alpha. So there is a symmetry. So from the symmetry, we can derive a further relationship, which we are going to do just now. So first, we look at sine of alpha. What is sine of alpha? Look at this. First, look at the upside triangle. Well, sine of alpha is this side by this side. So it is this part. Now, this part, let's call this as HYP1. So it is that part of the hypotenuse which is on the upside of the L perpendicular line. And HYP2 is that part of the hypotenuse which is on the downside of the L perpendicular line. The two together form HYP. So we can easily say that HYP equals to HYP1 plus HYP2. Now, for sine alpha, it is easy to see that sine alpha is equals to HYP1 divided by H. So that's exactly what we wrote here. But there's another sine alpha we can compute from this triangle. So you see this alpha, and the sine of alpha is given by H divided by HYP. Right? Yes, it is H divided by HYP. So we put that, okay, yes, indeed, sine of alpha is also H divided by HYP. But, but the thing is, if you, sine of alpha, yeah, yes. So now the thing is, if you use this particular view of sine of alpha, then the problem is the H is repeating in both. Now we don't want that. We want another independent measure of sine of alpha which does not involve the term H. So how can we do that? So now don't look at the whole triangle, just look at this triangle. Now what is sine of alpha? It is equal to this by this. So now this is the hypotenuse of that triangle. So sine of alpha equals to L perpendicular by W. So that's exactly what we wrote here. So in the first case we got sine of alpha is equals to HYP1 by H. In the second case we got that sine of alpha, we looked on this part of the triangle, is L perpendicular by W. So note the fact that we did not use the sine of alpha inferred from the overall triangle, because the overall triangle is actually composed of two triangles. So if we use the information from one of the triangles and the overall triangle, there's some kind of overlap. So we don't want to do that. We want to get some kind of independent equations that will lead us to the final answer. So we don't use the fact that sine of alpha equals to h by h by p. We instead use the fact that sine of alpha is equals to L perpendicular by W. And that's more important. We always need to break the given information into subparts such that each of the subparts is independent of each other. So we get independent equations. It's much easier to solve independent equations than dependent equations, because if there's a dependent equation, then you need to eliminate the dependency. So here, that's exactly the beauty of what we have done. We've just used two simple independent equations. Now, from the first equation, we can find a value of L perpendicular in terms of h, w, and h by p1. That's very easy, right? L perpendicular is simply h by p1 into w by h. And from the second one, we can find a value of L perpendicular in terms of h, w, and h by p2. So what is that? It says L perpendicular equals to h by p2 into h by w. Now, see the symmetry of this. See, what it says is that L perpendicular is given by h by p1 into h by w, or h by p2 into w. L perpendicular is given by h by p1 into w by h, or h by p2 into h by w. So there is a symmetry. Now also observe the fact that since L perpendicular is same, we can easily say that h by p1 into w by h is equals to h by p2 into h by w. So which means that if h and w are same, then h by p1 and h by p2 are identical. So that's easily seen from here. If the height and width are same, then the hypotenuse, then the whole triangle is split into two congruent triangles, two equal in every sense triangles by the L perpendicular line. So which means that if h and w are same, then h by p1 and h by p2 are same. And what happens to if h and w are different? Well, you can see very easily, if this line is smaller, then h by p1 becomes smaller, and that's also given by this equation, because L perpendicular is same. So h by p1 into w by h is equals to h by p2 into h by w. So therefore, if w is greater than h, then w by h is greater than unity, and h by w is less than unity. So which means that h by p1 needs to be amplified to be brought at par with h by p2. So you can see very easily there's a beautiful symmetry in this equation. All we are saying here is if the height and width are same, then the L perpendicular divides it into congruent parts, and h by p1 is same as h by p2. If they're not same, then it depends on how much h is greater than, or whether h is greater than w, or whether w is greater than h. If h is greater than w, then h by p1 is greater than h by p2, and if w is greater than h, then h by p2 is greater than h by p1. Now, of course, h by p, the hypotenuse, is the sum of the two parts, h by p1 and h by p2. So we get h by p equals to h by p1 plus h by p2. That becomes equals to L perpendicular by w into h plus w into L perpendicular by h. That is L perpendicular into h by w plus w by h. Now, L perpendicular into h by w plus w by h. Perfect. Now, what we can see from this equation, we can again get L perpendicular in terms of h by p, hypotenuse, and h by w, and w by h, or that is h and w. So L perpendicular is given by h by p by h by w plus w by h. Now, I would like to bring another thing to your notice, that the fact that the original right angle triangle has been divided into two right angle triangles means that we are able to actually relate this very much to this equation itself, because this equation says the sum of two squares is equals to another square, and here we are saying that the sum of two right angle triangles is equal to another right angle triangle. So there is a very much a parallel between these two relationships, and as we can see that we are coming closer and closer to this relationship as we are using these basic facts. The fact that the area is same no matter from which view you compute it, whether from this view or from this view, the base being the hypotenuse view or the base being the width view. So now you can see h by p is simply L perpendicular is simply h by p divided by h by w plus w by h. So we can say now that the two values of L perpendicular we have computed, one is this one, wh by h by p, and the other is h by p by h by w plus w by h. These two must be same. So we just equate the two. And you see immediately we can see there's a h by p square term that comes if you multiply this h by p with this h by p. So you get h by p square. Now this h by p square is equal to this product of these two terms. This is why are we doing this cross multiplication? Well, this cross multiplication is in a sense simply the unitary method. If you can just think a little deeper, that why when we have a by b equals to c by d, why we say AD equals to BC is basically something simply like unitary method. So we're just equating these two. So now what we get is h by p squared equals to w into h by w plus w by h, which is nothing but h squared plus w squared. So in a simple way, without constructing a lot of geometry, there's not much of geometry here. We haven't drawn squares on each of the sides, but we have simply proved that h by p squared, the square of the hypotenuse, equals the square of h plus square of w. And that is QED, Quod Erat Demonstratum, hence proof. Thank you all.